Perfect. So welcome everyone. It's a pleasure to have Taylor Hoyt here today. Thanks a lot for accepting our invitation. Taylor is a postdoc at the Lawrence Berkeley National Laboratory at the University of California, while he has his PhD at the University of Chicago, working with Professor Wendy Friedman on the tip of the Reggian branch and the Hubble constant. Taylor's research interest is in the measurement of extragalactic distances, making use of distance indicators such as TRGB, Cepheid variables, JEGB, and type 1a supernovae. Today, I will present systematics in distance ladder H0. Taylor, please, you can start when you're ready.
Thanks for the introduction and for having me. As Eleanor said, I'll be talking about some systematics in the distance ladder H0 because no talk could ever go through all of them, as many of us know. So I'll just go through some, I guess, that I've found most recently in recent analyses. So I'll just get into it. So I'll just briefly introduce measurements of the Hubble constant, its importance, the Hubble tension, as well as the relevant observables. I don't need to belabor that for this audience. Use my mouse. Then I'll talk about using the tip of the red giant branch and how it circumvents some of the many difficulties that impact Cepheid variables, the other competitive measurement of extragalactic distances. Then I'll present new distances and H0 results coming from observations from the James Webb Space Telescope. And I'll conclude with a new analysis of H0, I guess a new estimate of H0 that's currently blinded in the Union Unity framework, which is to do supernova cosmology, which will adopt the distances I talk about in the first part of the talk. So H0, the Hubble constant, why do we care about it? So of course, H0 relates a measured distance with a redshift at the present day for the present day expansion rate. The initial discovery of Hubble's constant ruled out a static model of the universe. That's kind of already our first instance of how this measurement helps us rule out or verify certain models, cosmological models. Okay, well, there's Hubble's law. Useful. Systematics historically have and can obfuscate the constraining power of the Hubble constant. This was seen quite famously in the factor of 2 debate over the value of the Hubble constant, which boiled down to really a debate over the age of the universe. It turns out that this was actually resolved in 2 parts. It was half new physics, the discovery of dark energy, which allowed for an older universe and a higher Hubble constant. And it was half distance measurement systematics that were resolved with the Hubble Space Telescope and the HST Key project. Today, high precision maps of the cosmic microwave background, in particular, it's 1 part in 100,000 anisotropies, paired the highest redshift observable at the last scattering surface, paired with H0, our lowest redshift observable, the present day expansion rate, provide our longest lever arm against which we can test cosmological models. Of course, right now the standard cosmological model is the lambda cold dark matter universe. So an empirical H0 experiment is almost exclusively focused on the measurement of absolute extragalactic distances, and that's what I'll be focusing on today. So a brief summary of what, I guess, how we do this end-to-end test and where things lie today. On the right, I'm plotting from the Planck collaboration's paper, the Hubble parameter as a function of redshift. The gray band is the lambda CDM prediction based on the CMB observations at Z of 1100. So H0 is, of course, on the leftmost y-axis. Overlaid are the SDSS BOSS BAO measurements. Presumably this could be updated with DESI, of course, but I don't know an easy way to do it. Someone who actually works on it could probably do so. And so if we add the Hubble constant measurement from shoes, we see what we define today to be the Hubble tension, which is this 5 sigma disagreement between the Cepheid-supernova measurement of the Hubble constant and the CMB prediction at the lambda CDM plus CMB prediction to today. And then if we add the Hubble constant measurement from the CCHP, this is the value from Friedman 2021, we see what I spend most of my time thinking about, and it's what I refer to as the local Hubble tension, or a tension within the tension. This is the disagreement between the values of the Hubble constant from the Cepheid supernova distance ladder and the TRGB supernova distance ladder. And frankly, this local Hubble tension needs to be resolved before we can actually assess the reality of the cosmological Hubble tension. And I just want to point out that these two measurements, though they seem to not disagree that severely, I would say the majority of the uncertainties are correlated between the two because they share the same geometric anchors and the same supernovae. So it's at least the same calibrator supernovae which dominate the uncertainty budget. So the disagreement is more significant than the H0 error bars would seem to indicate. So how do we do a distance ladder measurement of H0? In modern day, this consists of 3 rungs that span several orders of magnitude in brightness, starting from what we call a geometric 0-point calibration in rung 1, which includes distances determined through trigonometric arguments, most classically parallaxes, but other not as direct trigonometric measurements such as detached eclipsing binaries and megamasers also provide this to kind of round out kind of our 3 main geometric calibrations. These geometric distances are then used to calibrate what we call a primary distance indicator, like Cepheids or the tip of the red giant branch. And we use space telescopes such as Hubble or James Webb to then observe these primary distance indicators in supernova host galaxies in rung 2, the point of which is to calibrate the luminosity of the type 1a supernovae, which we then use to probe distances in the Hubble flow. So the part that I'll focus on here and generally is the focus of most of my work to date is the second rung, the calibration of supernovae. So both the the primary distances coming from the left side of rung 2, and more recently the supernova measurements on the right side of rung 2. As I mentioned, primary distance indicator calibrates the supernovae so we can use them as distance indicators out at cosmological distances. 2 main methods, Cepheids and tip of the red giant branch. Cepheids are young, massive, pulsating stars, easily identifiable given resolution and signal to noise via their very high amplitude sawtooth light curves as observed in the optical. They're located in dense star-forming regions of galaxies by necessity of their astrophysical nature. TRGB stars are the opposite. They are some of the oldest stars in galaxies and are located in the sparsest regions of them as well, or at least best isolated there. Various reasons are put forward for preferring one over the other, but really I want to focus most of the attention today on what I think is the most important distinction, the actual flux measurements on the CCD images themselves, which are vastly different for the two methods, based on the point above about where they are located in these astrophysical objects. So I'll qualitatively here show on the left measurement of a Cepheid in NGC 4258, which is the geometric anchor galaxy, one of the um, geometric calibrations in the first rung I mentioned before. You see the inset zooms into this region here in the central part of the galaxy. The local scene around the Cepheid, which is highlighted by the red and blue circles, just representing two different instruments of Hubble, and then zoomed in again around the Cepheid, again enclosed by the red circle. So there are a lot of sources around the Cepheid that may or may not be deblended in this galaxy. They are reasonably well deblended, but still there's significant scatter in the flux measurements. And this is the most nearby you can get for a measurement. On the right-hand side, I show a similar kind of zoom in to a TRGB field, also observed with Hubble at 11 megaparsecs, so slightly further than 4258. And the bottom right, you see a similar panel where the TRGB stars are highlighted with white circles. The average separation of the TRGB stars is about 2 arc seconds on the sky. So one TRGB, one source really every arc second or so. You can see just within this 2 arc second box, there are several dozens of sources near the Cepheid. So that gives you kind of an idea of the scale. A few versus a few dozens to 100 per arc second on the sky. And so I just want to show an example of how difficult these Cepheid flux measurements can be. This is NGC 5584, a Cepheid host at an intermediate distance, 25 megaparsecs. The galaxy is shown on the left with the Cepheids identified by the SHOES team with red dots. In the middle panel, I show the Cepheid period luminosity relation in the H band, which is where the band from which the Cepheid distances are derived once an optical reddening correction is applied. So in the top panel is the magnitude or brightness of a Cepheid, and in the x-axis is the log period of the Cepheid. The orange dots are the brightnesses of the Cepheids measured in the 2016 analysis from the SHOES team, and in blue from the 2022 analysis from the SHOES team. These are reanalyses of the same HST data, so the underlying data set hasn't changed, just the analysis. In the bottom panel, I show the per Cepheid difference in that observed magnitude. Here the residuals are in magnitudes. So one magnitude is a factor of 2.5 in flux. So the full range here is actually one magnitude. So the Cepheids, the estimated flux of these Cepheids from the same HST data, two analyses of the same HST data are varying by nearly a factor of 2 on the extremes. So in the average, if you just average over all the Cepheids, this corresponds to a 0.16 magnitude difference in the fluxes between the two analyses. This is also the exact same size as the Hubble tension itself. So it's about a 7-8% shift in units of distance. Exceeds the quoted distance uncertainty by a factor of 3. The distance, however, remained the same to within 100th of a magnitude, indicating the presence of other shifts in other areas of the analysis and also in excess of quoted uncertainties. This is one of the best measured Cepheid galaxies. It has the most densely sampled light curves at all band passes, so it should really be kind of the gold standard Cepheid distance measurement. And here I just show the same. So if you marginalize that bottom panel, and just plot up the histogram of the shifts in the magnitudes for 9 other supernova hosts. And the bottom right is our friend 5584 again. And so each title of each histogram is the percent change in the Cepheid magnitudes. And then right below that is the quoted percent error in the distance. So the ratio of the top and bottom number is the sigma shift. Kind of an underestimate actually of the sigma shift, since the bottom is the cumulative uncertainty per galaxy. So you see few to several sigma shifts for several of these that exceed quoted uncertainties. And my point here is that these measurements are just extremely difficult to make with HST. And so what can we do about it? I see there are really two main paths that can address this issue. One is a different method, the tip of the red giant branch, which does not suffer from the same extreme source crowding issues that dominate this Cepheid flux measurement instability. And the other is the use of the James Webb Space Telescope, which the significantly improved resolution relative to HST in the infrared reduces the Cepheid flux measurement uncertainties significantly as well. And this has been shown for a small subsample of the SHOES galaxies with JWST observations. So both seem very reasonable approaches to solving the issue. But I'll focus on the tip of the red giant branch. So here I show on the left the quintessential astronomer's plot that you will get sick of seeing by the end of this talk, with the luminosity plotted on the y-axis and the temperature on the x-axis, where cooler stars are towards the right. So what we see here is our red giant star evolving off of the main sequence. It's rising the red giant branch as its hydrogen shell continues to burn unstably and deposit helium ash onto the degenerate core. And if you watch what just occurred, that rapid transition off of the red giant branch and towards what we call the horizontal branch, or the red clump, is when the core reaches a temperature to burn helium. The core by that point is degenerate, and so the helium burning is a runaway because it's temperature insensitive, but the runaway only lasts a few seconds, because actually the input energy, which rivals that of a galaxy itself, is immediately absorbed, and degeneracy is lifted in the core for stable helium burning. So how do we observe this discontinuity? So this is the same plot, the empirical version of the luminosity temperature diagram I just showed in the typical Hubble Telescope band passes we use to observe the tip of the red giant branch. You can see the TRGB here, the red giant branch here, and the asymptotic giant branch above, which I won't get into, but just to guide the eye. So just to keep training your eye on what we look for to detect the tip of the red giant branch, it's this discontinuity at the termination of the red giant branch that occurs because the time scale for a star to rise the red giant branch is orders of magnitude longer than it is to evolve off. So you get this abrupt truncation in the counts of stars right at the tip. So the TRGB is kind of what we have that is nearest to a perfect standard candle. So the luminosity of the TRGB is actually dictated by the properties of its stellar core, which is mostly insensitive to the initial mass of the red giant star, so long as it is a low mass star, about the mass of the sun or lower. And there's a mild dependence on its metal content. So we have the M for magnitudes, more fun astronomers units, and then we have the metal abundance, also in fun astronomers units on the right. But the interesting thing is, it turns out at a certain wavelength regime, around 800 to 900 nanometers, called I band in astronomy, metals present in the star's atmosphere actually reprocess the flux and introduce a similar but oppositely signed dependence on metallicity. And thus, when observed in this I band around 800 nanometers, the TRGB is almost perfectly a constant luminosity. This is the basis for the most widespread application of the method with HST. We did this in 20 mid 2010s to 2020 in the Carnegie Chicago Hubble program, where we pointed Hubble at the square regions in the outer depicted here that lie in the outer regions of supernova host galaxies, to then detect the tip of the red giant branch here on the right. The TRGB is very cleanly detected in all of these galaxies. And that's what led to the result I showed earlier, of course. And what I want to get into here are new results from using the James Webb Space Telescope. This is a picture of my collaborators, In-Sung Jang on the left, Barry Medor, Wendy Friedman, Abby Lee, Kayla Owens, and myself. So the new results, we actually observed 3 distance indicators at once in 10 supernova host galaxies, and the geometric anchor, the Mega Maser 4258. You see them on the left. Again, here's more of astronomers' favorite plots. On the left are the color magnitude diagrams, the TRGB identified in red. And the band passes we observed in the TRGB is actually not a perfect standard candle, but it is standardizable via its color, because red giant stars actually have a very definitive relation between the color and the metallicity. The dispersion about the color metallicity relation is 3 to 400ths of a magnitude, which is about 2% in distance. It's a very tight relation to calibrate out the metallicity dependence. So some questions about the TRGB have been raised in the last few years that the high signal to noise data that we've acquired with James Webb addresses handily. So one is the variation of tip of the red giant branch magnitude within a single galaxy. Another is the reliance on a kind of author-chosen selection of the red giant branch on that luminosity temperature diagram I've shown. And finally, there's the metallicity dependence in the infrared, which I just briefly alluded to. So I'll get into how we addressed these in the James Webb Space Telescope analysis. So we had actually 3 independent fields, I guess, acquired with James Webb, of the geometric anchor galaxy NGC 4258. These 3 fields are depicted on the left, with what looks kind of like a crummy image of 4258, but I just set the stretch so that the bright, high surface brightness regions would saturate to highlight the low surface brightness regions in the exterior of the galaxy. So for reference, the Cepheid fields are effectively right in this bright region here, and there are a few fields also out here typically used. So the three fields are separated by about 10 kiloparsecs in physical size in this galaxy, so they're completely independent of each other. And you can see that the TRGB measurements portrayed here by the red bracketed lines. Quantitatively, the full range of the three measurements equals 0.071 magnitudes. Before we apply the infrared color standardization, and 0.058 after. That corresponds to about 3.5% and 3% in distance. In standard deviations, as much as you can trust them with N of 3, correspond to 0.029 and 0.024 magnitudes. But again, before and after the color standardization, those correspond to about 1% in distance. Another reassuring aspect of this analysis is that this dispersion within the galaxy that we observe in of the TRG measurements within this same galaxy are perfectly comparable to the uncertainties estimated on the tip magnitudes, which range from 0.024 to 0.030 magnitudes. So our uncertainties look to be quite accurate as well. So we do not see evidence for the large TRGB variations that were reported by CATS. Instead, we actually verified TRGB repeatability to about 1% in distance within a single galaxy. Next is the selection of the red giant branch. So here I show a color magnitude diagram from JWST from the Tully Fornax cluster program, and the selection of the RGB is shown as a gray band. Again, the x-axis is the temperature and y-axis the luminosity that we observe. What you can see is a fall off of the tip of the red giant branch towards higher metallicities. This is expected. Basically, once you exceed a certain metallicity, the standard candle postulate breaks down. And so that's why a selection of the more metal poor, bluer TRGB stars is necessary. However, as you can see on the right, this isn't really an infallible method, as there is actually a pretty competitive, equal amplitude peak situated near the preferred peak for the TRGB. So the question becomes, where do you set the boundary of this selection, right? Fortunately, the new solution implemented in the JWST TRGB analysis actually just retains the full color information. It does not rely on a color selection at all. If we zoom into one of the TRGB detections, I'll break it down. On the left is just the smooth, what we call Hess diagram. It's just binning up the scatter plot color magnitude diagram. Nothing special. And then in the second panel, I show kind of the actual phenomenological measurement used to measure the tip, which is just the two-dimensional vertical gradient, actually downweighted by the horizontal gradient to reduce noise from the edges of the red giant branch below. The result you can see here, basically the strongest contour, similar to the one-dimensional approach that's done. Basically the strongest discontinuity identified as the tip of the red giant branch. And we see it here plotted back on the scatter plot, where it very nicely agrees with what you would probably pick by eye as the tip of the red giant branch. So no color selection. Finally, the metallicity dependence in the infrared. On the left-hand panel, I show the brightness of the TRGB on the y-axis and the infrared color on the x-axis. You can ignore all the different points besides the filled points with black outline. and the black line that fits them. This is how we fit out the metallicity dependence of the TRGB. And on the right-hand side is a comparison actually of these new color-corrected infrared TRGB measurements with the I-band metallicity and sensitive measurements. And the agreement is quite good, about 1% or better in distance, which is about as much as we can say with just 6 galaxies to compare. But there's no evidence that there's an issue in the metallicity calibration. Let's see, I want to breeze through here, but essentially, as I showed, there were some changes from the 2016 to 22 shoes analysis. None of this is new, but essentially JWST confirmed what had been shown in Friedman 2019, that the earlier shoes distance measurements were significantly biased, and there's a distance-dependent bias within that, which you can see here, increasing distance. Some of these actually were biased by nearly 8 to 10 kilometers per megaparsec. This improved significantly in 2022, which is great progress for the field. The dispersion decrease in this comparison is a factor of 2 smaller. The difference between the two methods decreased by more than a factor of 2. So it seems we're headed in the right direction, very much so. And actually, this agreement improves even more if you regularize to the same geometric anchor. So this is kind of the most, I guess, expanded sample we currently have for comparing TRGB with Cepheids for 15 host galaxies. The agreement is sub% on the weighted average, and the dispersion is 5% RMS if you include all, and actually smaller, 3.5% if you just include the most nearby hosts. So it's all done and dusted now, right? So the Cepheid distances are confirmed. We can trust the H naught. Not quite. Only 15 of the 37 Cepheid host distances have been checked by CCHP with TRGB. 4 more are partially released in the JWST data archive, and analysis is expected. All remaining Cepheid distances to be checked are actually located twice as far on average than those that have already been checked. Let me show this on the right. So the blue histogram shows the distribution of distances of the Cepheid hosts that have been checked with TRGB, which I showed in the previous plot. And the orange histogram shows the Cepheid hosts that have not been checked by TRGB. You can see they lie at significantly greater distances. And of course, that means crowding uncertainties will increase considerably as 1 over d squared. So we need to complete this check with JWST. A single medium program would be able to achieve this. So I say, let's do it. So what about H naught? So again, there's the H naught from REES 22, and then the CCHP H naught didn't change much from 21 because we really only added 4 supernova hosts. So the question still remains, what's causing this disagreement in supernovae, or in H naught for the supernova distance ladder? So TRGB and Cepheid distances agree now. Why is the H naught value still separated by 3 kilometers per second? Something's got to give. It's in the supernovae. And so briefly, so in the left panel, here I'm just showing the per galaxy shift in the Cepheid distances from pre-2022 shoes to 2022. And in the right-hand panel, the change in the supernova magnitudes. More things changed as they improved many aspects of their analysis. These are just the kind of the most important. So basically the magnitude of the supernovae changed. That's why, despite the improved agreement of distances, the H naught values still don't agree. And so I really want to get into the supernova work that I've been doing with my collaborators associated with either previously or currently at Berkeley Lab. And what we're working on is incorporating H-naught into the Union Unity framework for doing supernova cosmology. This two separate pieces. Union is a compilation of surveys that was initiated to combine supernova measurements from various surveys to constrain the dark energy equation of state. You could almost think of it as a distance ladder in redshift, where what you're laddering is the calibration of different surveys that cover different ranges of redshifts. Um, so Unity is the model framework that, or the framework that models the supernovae data compiled in Union. So Unity is a Bayesian hierarchical model intended to uh, capture complex effects such as selection effects, outliers, outlier, outlier contributions, uh, redshift evolution of standardization parameters, underlying 1A population distributions, etc. The Union Unity framework shares many traits with Pantheon, uh, which is I highlight just because it's the only multi-survey analysis that has been used to measure H-naught to date, and it also has some key differences, uh, some of which I'll get into later. So briefly, I'll summarize key results from the most recent Union Unity implementation. So there's a significant detection of a split in the color standardization of type 1a supernovae, and a further correlation with host galaxy stellar mass, which is consistent with Pantheon Plus findings. Uh, a small and low significance measurement of residual bias related to the host galaxy stellar mass. No detection of an evolution of that mass step with redshift. Early hints of evolving dark energy that were later strengthened by DESI PAO, and pointing out that local H-naught measurements increase the dark energy figure of merit between 10 to 40%, depending on which H-naught value one takes as an external constraint. This last point kind of leads naturally into, rather than taking H-naught as an external constraint, actually include H-naught in the simultaneous solution. So how do we do so? There are really only two key additions to the Union compilation, that is light curves for calibrated supernovae that were not already included, which are just a few that were part of surveys that were included in Union 3, but that were published as standalone papers. And then the kind of more extensive addition is the determination of stellar masses for several hundred supernova host galaxies. And then Unity, only small updates with, on the host mass correlation. I don't get too into that. I'll get into that later and introduce what even the host mass step is, but that's explicitly fit for rather than held fixed. So why do we bother estimating the stellar mass of supernova host galaxies? This is a plot from Rigaud 2020 that plots what we call the Hubble residual, or identical to delta MB core, which is just the corrected standardized magnitude of a type 1a supernova as a function of stellar mass of the host galaxy on the x-axis. You can ignore the colored points for now, but essentially what this shows is that there is a discontinuity in the predicted distances after correcting for the canonical stretch in color that remains in the Hubble diagram, and seems to have a discontinuity at about 10 solar masses. This is pretty conventionally fit for and removed in modern supernova analyses. So why does this kind of bizarre step in the Hubble residuals actually exist? Well, if we look here, this is a plot of the star formation rate per stellar mass for galaxies on the y-axis versus the total stellar mass on the x-axis. What you see are kind of the two main populations of galaxies in the universe. On the top, you have what's called the star-forming main sequence, and on the bottom, you have quiescent galaxies. And this phase transition between the two is extremely rapid, just like we see in the stellar mass. So how do we derive these stellar masses? Essentially, some uh, basis functions for galaxy uh, SED and suite of stellar population synthesis models are used to generate model spectra, which we can then use to fit to photometry of the host galaxy, like I show here. So I'll show three examples of the three kind of main regions of this, the galaxy population. So here's a low mass star forming galaxy with the new SED fit shown here, which is just the flux. And here's UV bands, optical, and near to mid infrared. Here's a high mass star forming galaxy. Uh, Same bands, good fit again. And then here we have an elliptical. Here you can see there's little dust, which reduces the emission that you see here in the mid-infrared. So quickly, well, I made sure to have a validation sample where I cross-check the new mass estimates with existing mass estimates compiled in Union and find a 0.09 dex offset with SDSS masses with a 0.1 dex dispersion. This is more than sufficient for cosmology. We'll see later that systematics of this kind have to be larger than 0.3 dex at least to correspond to about a 0.01 magnitude distance bias. So I won't belabor this too much, but the new mass estimates tightened up a lot of the host mass dependent parameter constraints we have in Union, which I think is a good validation that the new masses do fit into a homogeneously into the same system as the existing masses. Briefly, these are just corner plots we have from the blinded unity analysis so far. We're expecting a 1.7, 1.8 measurement of H naught percent. I think I have to say percent. I won't get into too many details there. And then finally, I just want to conclude with why we might expect this independent analysis to be interesting, even though we're going to be using the exact same shoes, Cepheid distances, and CCHB TRGB distances. So we're using a different model, a different SALT model, SALT 3 as opposed to SALT 2.4. Independent host mass estimates, a larger Hubble flow sample, and the rest are kind of smaller. So I'll just focus on the top two there. So comparing SALT 3 or comparing Union versus Pantheon, if we just compare the color inferred of type 1a supernovae, and we break that into the calibrators, which set the 0 point of the Hubble diagram, versus the flow sample we call the cosmological sample, we do actually see a differential offset between the two. And the immediate question is, well, I guess I'll explain, but differences in the average light curve parameter uh, between the flow and calibrator sample propagate as a systematic in H naught. So what this is telling us is that SALT 3 is measuring redder colors for calibrators than it is in the flow sample for Pantheon, comparing Union and Pantheon. So the question to ask is, how much is this due to just the difference in the SALT models? So we tested that directly. And so if we compare actually Union to Union, but instead SALT 3 to SALT 2.4, we actually see a very similar difference. So about 0.01 difference in the inferred supernova color. So compare with the Pantheon comparison, there's really only probably a few thousandths of a difference in the color C, the salt color. So seeing where that ends up in terms of H naught will be interesting. since there seems to be a real difference between SALT-3 and the calibrators versus the flow sample. So there may actually just be something non-representative in the calibrator sample, which is kind of what everyone would agree we're afraid of, but it might just be the case, and maybe SALT-3 does a better job at standardizing them or not. We'll see once we unblind and investigate everything. So the other point I want to raise is what fell out while doing the host mass estimates is um, a kind of concerning discontinuity in the Pantheon mass estimates that I saw. So what I'm plotting here is the difference in mass, host mass estimated, the stellar mass estimated to supernova host galaxies between Union and Pantheon Plus on the y-axis. So these are the residuals. And on the x-axis is the redshift. um, so for low redshift galaxies, Pantheon Plus redetermined the masses using their own methodologies. And those are shown, the comparison is shown as the orange circles. And then for high redshift, they returned the masses that they extracted from original publications. So Union also pulled the masses from the same papers. So that's why you have the exact agreement on the zero line. So you're seeing the left-hand side is also a comparison of Pantheon Plus against the SDSS SN masses. So essentially what you're seeing here is an internal systematic disagreement in the host mass estimates in the Pantheon Plus compilation. And then for reference in the orange triangles, I show the difference between SDSS and Union for the new masses determined and added there in the validation sample. So you see a much tighter agreement. So in the Union masses. So the problem is this introduces a systematic offset in their host estimates that even makes them inconsistent within the same survey. So if we just keep adding more surveys to see if this persists, we'll see that it does. So here we had SNLS. It's only high Z, so we don't see the step, but we do see the confirmation that Union and Pantheon pulled from the same paper. So then we had pan-stars. Again, mostly agreement with some scatter. Maybe Union pulled some different sources for those masses. But still we see the same step between the newly determined Pantheon masses versus the original published masses. This persists when you add foundation, CSP, and loss. So in the end, this 0.5 dex systematic bias in Pantheons persists. It destroys internal self-consistency within and across supernova surveys. The effect, if we actually just integrate over the Hubble diagram, amounts to flipping 20% of supernovae from high to low mass, which propagates as about a 1 to 200th of magnitude bias in Hubble residuals, which would correspond to about 0.3 to 0.6 kilometers per second in units of H naught. To exactly compute the effect would require an end-to-end reanalysis of Pantheon Plus. So redoing down to the BBC bias corrections with updated masses and arguably a floating mass step if there's a half a dex disagreement between how they're doing their masses versus how these literature values were derived. We can actually estimate the effect to be about 0.018 mag if we use the Vincenzi 2024 findings. So they found about 100th of a magnitude, actually exactly 100th of a magnitude difference, whether or not they adopt the Pantheon Plus masses. And if you compare the DES masses to Pantheon, it's about a 0.3 dex offset from the low and high redshift bin. So if we just scale it up to 0.5 dex, you get 0.018 mag, or actually 0.016, sorry. But yeah. So finally, some additional mysteries would actually be explained by a Pantheon plus mass bias. So here I show a plot from DESI that shows the distance modulus residuals about a fiducial cosmology, which in this case is CMB lambda CDM. So essentially everything you see here off of zero is a departure from lambda CDM. So the left panel is the DES 5-year survey projected onto this plot in gray points. Middle panel is Union 3 Unity, and then the rightmost is Pantheon Plus. I really want to draw our attention to the right two panels since about 70 or maybe even 80% of supernovae overlap between Union and Pantheon. So essentially the points should really track very tightly, but they do not in the lowest redshift bin. They differ by about 400ths of a magnitude. But the other points agree fairly well, maybe 200ths. And then especially in the intermediate redshift range, the agreement is exact. So, well, I didn't include it, but right. So if you add that 0.016 shift, then the Pantheon point would pull up here, bridging about half that difference you're seeing in the low redshift bin with the other two surveys. So summary takeaways, I'd say Cepheid distance errors are likely still underestimated. We need to complete the TRGB comparison. Self-consistent host mass estimates are essential for accurate supernova cosmology. Calibrated supernovae do not appear to be representative of larger Essen samples still, and that I base that off of the SALT 3, SALT 2.4 difference. Several key differences between Union Unity and Pantheon Plus, and the supernova analysis suggests we may yet learn something new and interesting despite both using the same published calibrator distances. And that's all.
Thank you so much for the nice talk. Do you have any questions? Dan?
Yeah, hey Taylor. I should want to give maybe a bit of a surprising comment. I really appreciate your talk. I just thought it was really nice, and you're doing due diligence where we need it. I hope Dylan can talk a little bit about the mass step stuff. But I put a comment in the chat about Wendy and I are discussing the difference between photometry versus distances. But I just want to say I really appreciate your talk. All right, I'm gonna pass it. Maybe Dylan can talk.
Yeah, Dylan?
Sure. Yeah. Thanks, Dan. And thanks, Taylor. I totally agree. I really appreciate when people are digging and you're doing that, and that's important for pushing things forward. So just first off, thank you. In terms of the mass steps stuff, I think you alluded to it. Maybe you could go back to this slide that covers it. That, or yeah, that one. Thanks. A couple of things. So you already alluded to it, and so thank you for alluding to it. But I wanted to just sort of reiterate. It's important to do this like all the way through the end-to-end, pipeline, so to speak. Although we've taken some steps to try to make this possible to do. And so I went ahead and checked this claim, and when it comes to H naught. I guess it's not exactly true to compare the 0.01 mag or 0.02 mag bias that you say and convert it into H naught units, right? You need to do the distance ladder part, and you can do that, and it comes out to 0.001 mag in when it comes to measuring H naught, because it comes from the difference between the calibrators and the Hubble flow, all of which are to the left of that vertical line you've drawn. And so that's
if I
like.
can add, I
Yeah.
did actually do the comparison of calibrators, and we actually didn't see a bias. So the Union Pantheon comparison does not have this 0.5 dex bias. In fact, our masses agree exactly for the calibrators. So it is purely the Hubble flow sample.
Okay, well, it would be important to show that to back out the impact on H naught. The other thing is, again, if you plug it into the Pantheon Plus formalism, and I have a notebook, I'm happy to share it with you. It's more like 0.01 mag in the low Z bin for measuring evolving dark energy. It's much less closer to 0.02 mag when I look at this effect. So yeah, if we're talking about 0.01 mag effects, I'm happy, and I think that's where this sits right now, and certainly motivates more work. So thanks.
Thank you. Sean?
Hi, thanks. So, hi, this is Sean. Thank you for your talk. And so, earlier in your talk, you had mentioned that the Cepheid analysis can be very difficult to do, and you argue that you saw changes in the Cepheid analyses over time. And again, there's a great discussion in the chats. Would you agree that the same could be said for the TRGB? In particular, there's about a tenth of magnitude shift between the unblinding in your work and also the posted iteration, as well as a subsequent 0.02 magnitude change between posted versions 1 and 2. And of course, I encourage people here to kind of pull up the data in the papers directly. In other cases, for instance, DESI had changes between version 1 and version 2, Planck as well. And so is there any argument for why those changes and changes in your analysis would be more acceptable compared to the Cepheid analysis from Shoes?
I don't actually know what version differences you're talking about, or a tenth of a magnitude shifts. I've actually never, I don't know what you're talking about. So the one thing I would mention is, so in the comparison with HST and JWST, there was actually a kind of, I think about 1.5 sigma shift, but still an absolute value shift in the distance of 5643. I think there's something funky actually going on in that galaxy. I think EDD, Annan's measurements actually corroborate that too. He's found a similar disagreement from JWST and HST distance measurements. But other than that, I don't know of any, 3, 4 sigma shift. So recall the shifts I was talking about was actually in the photometry. There hasn't been any shift in photometry for the TRGB that has ever approached that level. So it's just not true.
Pilar has a question.
Yeah, thank you very much, Taylor, for your talk.
Oh, hey, Pilar.
I want to come back to this statement that now there is an agreement at the nearby distances between TRGBs and Cepheids. I don't think that this is happening. Actually, I see that the two groups, the Shoes collaboration and the CCHP, are agreeing very much in Cepheids, but when you compare the TRGBs with the Cepheids for very low distances, like for NGC 5643, you get a difference in magnitude of larger than 0.06. I mean, right now, your latest value for this distance is 30.643, whereas the Cepheid value is 30.57, 30.58, and the TRGB value by the Shoes collaboration is also around that level. So there is a huge disagreement, and I don't understand where is the problem. Maybe it's in the ambiguity in the line that this red line that you have to place for the TRGBs in signal in the tip of the radiant branch. I see that some slopes have a stronger slope than others for different TRGB TRGB values. Is this the problem? I mean, the ambiguity on the line.
So the different slopes, I should actually have, I'm gonna stop and I'm gonna go to my supplementary slides. I just can't see the sidebar. Sorry. It's a good question. It's just what I was talking about with the 5643 shift.
I just wanted to point also that only a few months ago, the value was 30.61 by your collaboration. So I don't know why it went up like 0.02 more in 3 months.
Yeah, that was from an updated standardization of the IR color. But I mean, that's like a 0.2 sigma shift, but so this in the, can I zoom a little more? So in the bottom left here is a plot of, again, the tip of the infrared TRGB color that we use with James Webb, with the IR color on the x-axis, and plotted our isochrones from ages 4 to 10 gigayears in 3 metallicity bins, which are chosen to span the full range of our JWST observations. And what you can see is that essentially it's how the age effects change as you change the metallicity that will affect the slope. But in the methodology that I implemented for measuring the tip, what I actually constrain is the locus of the TRGB. So the slope is just a nuisance parameter. The slope measured in each galaxy is just a nuisance parameter marginalized out, whereas what's used to standardize is actually the sample-wide average slope, which is represented by this dashed black line here. So the idea is that the age, the variations in the slope,
I think
would be
these
caused
kind
by
of
age effects are
differences in the TRGB measurements are the ones that are giving the main difference in the values of H naught at the end when you propagate the calibrations on the supernova at larger redshifts. Those make a very large difference. I have tried myself and I saw it. It's not so much the supernova sample.
Which supernovae are you talking about?
On this one, on the one, for instance, in the NGC 5643
Right, you
host
mentioned that galaxy
supernova.
already, but what about any, because there's 24 supernovae.
Yeah, but this happens with many others. I just
Which
quoted this
others?
one
I
because
don't,
this is at a very low distance. And
but
since you
it's
said
not,
there was
but that's
agreement,
not true of others. I don't know. 5643, yeah, I actually have a slide that I dedicated to that shift because it's the largest shift I've seen in our TRGB distances. But all the rest, no, that's just not true. That is the largest shift de facto.
well, yeah, I think one has to reconsider this perhaps. But thank you for your
Reconsider
answer.
what?
Thank you very much for your answer.
Thank you. Are there any other questions? I see many in the chat. Maybe someone wants to.
Oh, I'll read the chat. Sorry.
Yeah, I can go ahead. Nice talk, Taylor. This is deep. Yeah, so it looks like you just touched upon it with the previous question a little bit, but just to reiterate, so there's a factor of 5 difference in the measured slopes within the 3 fields in NGC 4258. So how do you square this with the near-IR TRG being a tight relation, and doesn't it imply that there's at least a very large scatter in that relation? And similarly, in your 2024 paper, you measure a slope of minus 0.99 in NGC 4536, but your newer paper has a slope of minus 0.33, which is a factor of 3 shift from the same data. So do you know what caused the drastic shift there? Because it's a bit worrisome.
So first, it's not the same data, and it's a different methodology. So in fact, the mapping, so the methodology used in that paper is actually, I would say, outdated. And I think other experts on TRGB would agree that actually trying to map stars identified at the tip of the I band to the infrared actually introduces a lot of scatter. So the tip is not defined by the actual same physical stars. And also the number statistics were about a factor of 4 worse in that paper because it was limited to the overlap with HST. And in terms of the slopes, so let's see. Let me pull up, sorry, sharing the slides again. So if the different slopes actually led to biases in the measured tip, then why would the tip measurements actually come out to agree to 300s of magnitude before color standardization and 200s after? And regardless of the before and after, the agreement is 300s.
Yeah, but if they're offset by, if the slopes are offset by a factor of 5, it means there's huge scatter in the relation, and it just, 3 fields is not enough to then figure out what your true slope is or what your true scatter
But
is, right?
I don't use 3 fields to measure the slope. It's 13 fields to measure the slope.
Right, but in your calibrator galaxy where you have the highest signal to noise data,
But
or about the highest signal to
the
noise
slope
data,
is
including
not, so
M101.
the slope is not measured from the individual galaxy. It is not an average of the individual slopes. It is a sample-wide average of the TRGB locuses. So,
Okay, but maybe I'm misunderstanding something, but in your table 2, you have slopes listed for each galaxy.
yes, and those are just nuisance parameters because in order to do a two-dimensional fit with an ellipse, you have to have a slope, i.e. a position angle. Those are not used anywhere in the analysis. It's just the color magnitude ordinate. But to actually get
Okay.
an unbiased estimate of the color magnitude ordinate, you have to include a slope as a parameter, as a nuisance parameter. The individual slopes are not used. So you really shouldn't be doing that. That will bias you if you try to use some single slope, right? If you try to extrapolate, like you seem to be pointing out, if you try to use the right-hand slope to, really interpolate there at the same colors to the left-hand slope, yeah, you would have a bias, but that's not what I do. And I think I've heard this repeatedly. I think maybe this is a misunderstanding you have of my methodology. Only the central value of the ellipse is used in any of the distance analysis. So that
I guess
places
all I
each
have to
dot
say
on
is I
this.
think it's telling us something about the physics that's going on if the slope is varying by a factor of 5 in the same target in 3 different fields. I get that you're sort of using the average slope at the end, but it's telling me that there's more scatter.
But can you tell me how that propagates into affecting the distances? I agree. I think there is astrophysics there, but the point of the method is to minimize the astrophysical effects, and it works.
Okay.
If it didn't, then how could the comparison with HST come out this way?
Okay, and I just had one more follow-up. So you've done a lot of work, a lot of good work going in and digging into the shoes photometry, as you did covered in the first part of your talk. Are there any plans to release the CCHP photometry dating back from 2019 so that the community could do some similar checks?
I think you have an office mate. So the CCHP 2019 photometry was actually done by Rachel Beaton, who's down the hall from you. You could probably ask her. I don't have proprietary access to that data. And the JWST data photometry will be released upon publication of the paper. So there's your answer.
We could thank Taylor. Thank you so much.